Sometimes when we compute a definite integral, when we find the area under a curve, we don't care about an exact answer. We're okay with approximations. In that case, we could do something called a Riemann sum. A Riemann sum is where we take the area we're looking for and we approximate it by considering it as the sum of a bunch of rectangles. For instance, I can use these four rectangles. The area of these four rectangles is going to be approximately this blue area that I'm looking for. The question is, how tall should I make the rectangles in order to make this work? A logical answer might be, maybe I should line up the middle of the rectangle with the function. Between 0 and 1, I use f of a half to determine the height of my rectangle. Between 1 and 2, I use f of 1.5 to determine the height of my rectangle. Between 2 and 3, I use f of 2.5. Between 3 and 4, I use f of 3.5. This is called a midpoint Riemann approximation. It's not the only way to do it, but it seems kind of a straightforward way to do it, especially given this sort of shape. Other graphs that might not jump out at me. This is an okay approximation. The idea behind Riemann approximations is that if I have enough rectangles, my approximation gets better and better. Here, with my four rectangles, my approximation is already only like 0.1, 0.11 away from correct. But if I, instead of four rectangles, if I kick it all the way up to, let's say, 50 rectangles, now it looks like I'm right to the tenths, hundredths, thousandths. I'm less than 1,000th from a correct answer. So I'm pretty good now. A computer, I imagine, wouldn't do 50 rectangles. It would do 5,000. So a computer could approximate integrals in this way. Enough blabbering on. Let's see how this actually turns into problems. One problem I could have is approximate the integral from 0 to 4 of x squared, so area under x squared between 0 and 4. Here's 0, here's 4. I want to approximate this area using, it says, two rectangles. It doesn't tell me my rectangles have to be equally wide. I'm going to use two equally wide rectangles. So one of my rectangles is going to go from 0 to 2, and the other rectangle is going to go from 2 to 4, just to make them evenly spaced, but it doesn't have to be for a Riemann approximation. The height of my rectangles, I'm going to find by using the midpoint. Between 0 and 2, I'm going to use f of 1. My rectangle is going to line up so that right at the point 1, comma 1, that first rectangle hits it. My second rectangle, I'm going to use 3. I'm going to use the midpoint of the interval 2 to 4 to determine the height. So this rectangle is going to go all the way up to here. This rectangle goes all the way up until it hits the point 3, 9. So I can approximate this integral as the sum of the area of these two rectangles. The first rectangle has a width of 2 and a height of 1. The second rectangle has a width of 2 and a height of 9. So overall, my approximation comes out to 20. That's the approximate area. If I actually go and do fundamental theorem of calculus to find the actual area comes out to 21.3. So my approximation was pretty good. I'll settle for that, off by a third, or 1 1/3 rather. Similar problem. Here I'm approximating the area under the graph of square root of x. So I've got square root of x between 1 and 13. And this time it wants me to do it with 3 rectangles. Again, I'm going to do equally spaced rectangles. So to get from 1 to 13 in 3 intervals, I'm going to go 1 to 5, 5 to 9, and 9 to 13. And I'm doing area under square root of x. My first rectangle, to approximate this area I'm looking for, my first rectangle is going to go from 1 to 5, and its height is going to be determined by f of 3. it's going to go all the way up to the point 3 comma square root of 3. My next rectangle is going to go from 5 to 9, and its height is going to be determined by f of 7. So it's going to look something like this. Squint a little bit as you watch this. That way you believe that I'm drawing straight lines. You would never believe I'm making this on a computer, given how totally inaccurate everything is. Between 9 and 13, I will draw a rectangle, and its height will be determined by the midpoint between 9 and 13. So its height will be determined by f of 11. So it's going to go all the way up to here, like this. So I'm going to approximate this integral as area of the first rectangle. The first rectangle is 4 wide and square root of 3 tall, plus area of the second rectangle. The second rectangle is 4 wide and square root of 7 tall, plus area of my last rectangle. My last rectangle goes all the way up to the point 11 comma root 11. So this rectangle is 4 wide and root 11 tall, and I already did the math for us. It looks like this comes out to 30.778, when the actual answer, if I actually did fundamental theorem of calculus, would be 30.581. That's a phenomenal approximation. Before I move on, I do just want to show how I would have actually written the math myself. If I were doing this, you see how the width is the same for all the rectangles. Since it's the same, I would have written my work as 4 times root 3 plus root 7 plus root 11. I know it's the same thing. Obviously, I could just factor a 4 out of all these, but I would have never written this line in the first place. I would have written this line, the width of the rectangle times the height of each rectangle added up. It just saves a second if I'm doing it by hand. One more, and then there will be one more after that. So 2 more. 2 more is 1 plus 1 is 2 if you don't have a calculator handy. This second to last one, I'm doing the area under the graph of 1 over x between 2 and 22, and I'm breaking it up into 5 rectangles. From 2 to 22 is 20 units, breaking that into 5 pieces. Each one has to be 4 wide, so I go from 2 to 6, 6 to 10, 10 to 14, 14 to 18, and 18 to 22. So, and I'm doing the area under the graph of 1 over x. My first rectangle goes from 2 to 6, and it has a height determined by whatever f of 4 is. Then I've got a rectangle that goes from 6 to 10, and its height is whatever f of 8 is. Then I've got a rectangle that goes from 10 to 14, and its height will be determined by f of 12. A little higher, let's say, like that. And then 14 to 18, and I use 16, f of 16 to determine its height. At this point, my drawing is too bad to really tell. 18 to 22, I use f of 20. So, my approximation for this one is going to be, first rectangle is 4 wide, and this is the point 4, 1/4, so it's 1/4 tall. My next rectangle is 4 wide, and its height is 1/8. Then I've got one that's 4 wide, and this shows what I said last time. I'm running out of space. I'm just going to factor out a 4. and add the height of each rectangle. Everything is 4 wide, so I do a width of 4 and height of a 1/4 is my first rectangle. My second rectangle has a width of 4, height of an 1/8. My third rectangle's area is going to be 4 times a 12th. The next rectangle's area is 4 times a 16th. And the last rectangle's area is 4 times 1/20. This comes out to 2.283. The actual area, if I were to actually do all this area, comes out to 2.398. So again, phenomenal approximation. Sometimes I don't have a function. Sometimes I'm just given a table of values. In this case, I just use the values they gave me in a way that I will now demonstrate. Here they want me to use midpoint approximation to find the area between 2 and 10 and 2 rectangles. So if I'm equally spaced, I'll go from 2 to 6 and 6 to 10. And the height of each rectangle is going to be determined by the midpoint. So like this rectangle is going to have a height determined by whatever f of 4 is. This rectangle is 4 wide and f of 4 tall. Then I have a rectangle from 6 to 10, and its height is determined by the midpoint of that interval. Its height is going to be determined by 8. This rectangle is 4 wide and f of 8 tall. So in total, the sum of these areas, the areas of these rectangles, is 4 times 1 plus 4 times 8. This comes out to 4 plus 32. 36 is the approximation for this. This is getting to be kind of a long video, but if you'll indulge me for just another second, I want to show you that sometimes midpoint approximations aren't that phenomenal. If instead of a function like this, if I had a function that looked like this, if I could get, there we go, this. Say I want to approximate that area, and I used a midpoint with 4 rectangles. Well, between 0 and 1, I use f of a half. Between 1 and 2, I use, almost there. Oh, so close. Oh, don't fail me now, computer. I use f of 1.5. Between 2 and 3, I use 2.5. You see where this is going. Between 3 and 4, I use 3.5. Clearly, the green area isn't hugely under approximation of the purple area. But again, the idea is that with enough rectangles, the fact that some functions don't work well with midpoint doesn't really matter. Enough rectangles, and we get a phenomenal approximation.